quite a bit of research out there about the misconceptions, and it turns out a lot of the ideas that students get wrong are really well entrenched, and they're things that are just very difficult for them to shake, and they're very difficult skills that perhaps we maybe rehearse, maybe do not rehearse as often as we like. So there are a number of resources up here, a number of issues that I would suggest are kind of the long-term pieces. So we can take a look at the state data, which is a summative assessment, and then kind of place that in context of how we might use it during the year. One of the things I'll ask you to think about is what's the emphasis, what's the bottom line that we want our students to get from the various activities and things that we're doing. Are we more concerned about the technical skills of collecting the data, the overall skills of how do I analyze something more, that nature of science piece, if you will, how we analyze data, or is it the final understanding that we're looking at? And those are all slightly different issues. If it turns out that a student can't answer a graphing question, it could be a technical skill that they don't have, or it could be not understanding what that overall nature of science is, the whole process of that. So we'll go through it and hit a few of these. Some research from the 60s that I like to refer to. My dissertation advisor was Dr. Pella, and research from the 60s suggesting that it's not easy for students to glean all the steps of the scientific method. In fact, the most difficult part of that whole piece tends to be that first one, the statement of a problem. So one thought is, both vertically as they go through the various grade levels, and horizontally over the course of the year, how are we moving them forward from something that's highly structured to something that's less structured, a little bit more open-ended, how are we going to move them forward in terms of how they're thinking. I had mentioned misconceptions. Paige Keeley from the Maine Department of Education has come up with, I can't even tell you how many of these books that she's identified, a number of probes. I put one example up here. This was related to the question about whether magnets can work in water or do they work in air. And she has elementary students exploring this. She has a number of books. Each of them are about 25 different probes. There's a delightful set on density. Students have a number of misconceptions related to density. Very first question in there, she takes a log and shows it floating in the water and asks, what happens if we cut a small piece of the log off? Is it going to float higher? Is it going to float lower? And then goes through a number of iterations of that. The very last question in that series of probes is one where she takes a block, drills holes in it so it looks like Swiss cheese, and then the question is what's going to happen to the density of that block as it floats. So just getting at that fundamental misconception, it's really a neat way to do it. In this case, she has several different students stating various misconceptions, even though she doesn't call them that, and asks her students to write a little bit about these, to select an answer. So it's another way at some of the same ideas that we'll be, to get at some of the same ideas that we'll be talking about this morning. Item difficulty is not an easy thing, and I guess I'll just kind of leave it at that. It's not easy to predict, and the numbers that I'm going to give you are going to help us to get a handle on it, but they won't necessarily be definitive in terms of giving us an absolute value. We're going to take a look at the item difficulty, and I'd like to go through a discussion with you about some of the current approaches we're taking. The next steps would be kind of back to that book I just mentioned, or some other resources like that, generating some items that you might use in the classroom to get at that same idea, and then taking a look at how your students are doing following the new instruction and putting the pieces in place. Once again, the alignment between curriculum instruction and assessment. And in case somebody has not pointed out to you already, the Next Generation Science Standards draft was released last evening about 5 o'clock, 2 minutes before business closed, I think. They're going to be online. They're looking for input from the field through June 1st, I believe. So it's a relatively short window, fairly early in June. But those are available and they are online. We're going to have to go through some type of realignment with the curriculum in the next few years for sure. We'll talk about knocking those and those forward. And I'm certain all of you are well entrenched with the literacy strand in the LA for reading and content areas. Certainly hearing about that. Three numbers that I'd like to talk about. A set of 10 students take a test. If I was going to put a number on this, how many students got this question correct? According to the slide, if the answer is the correct one. 5 out of 10, so 50%. We can think of that difficulty as being 50%, and I know it kind of sounds backwards, but 50% would be the percentage answering the question correctly. We can talk about it as being a 0.5. I usually show it as an decimal equivalent. It's easy to do. Two other ideas that I'd like to think about. One idea is this. How well does this item predict the students that are going to do well on the test? Well, if I take a look at this, the students that got this correct were students that got 100, 95, 90, 88, 85. So at least the upper half was right. The students in general that did poorly on the item were those that scored a little bit lower. And basically discrimination is talking about a correlation between how did students do on a particular item and how did they do on the test as a whole. So it's one more number that we can kind of use to judge whether an item is valid. If we take a look at an item and the discrimination is very high, and there's a correlation I'd expect it to be, in social science we usually use about above a 0.4 as kind of the platform, but closer to 1, higher up would be a higher one. If it's high, it tends to indicate that students who did well on the test did well on the item, meaning they're testing the same thing. And if it's a low number, it tends to indicate that either students who did poorly on the test did well on the item, or there was no correlation between these two, meaning there was something else going on. So maybe it was a point that I covered while part of the class was out for an honors field trip or something like that. Then they missed those particular items. The third thing that's important to take a look at, are the responses that the students are coming up with. If you didn't select A, the more critical part is going to be what did they select other than A, or whatever the correct answer was. And then that can lead us into some interesting discussions of why is it that they chose that particular answer. Is there something technical with the mathematics, with the arithmetic skills that they have, or was there some other issue that was going on? If you take a look at the yellow pages in front of you, there are two examples that I've kind of latched into one page. The first page is two-sided, and there's a specific number of items that we're going to be going over. And if you look, I've shaded very lightly down the column, just about at the bottom of the page, in that item number. I've shaded the items that we're going to be taking a look at on here in a little bit. But this starts out right at the top. Let's see, I have my alignment off on the first one. So the very first item that's identified here is number 9 on the June 2011 exam. It's a multiple choice item. It tells me the difficulty is 0.3, which means, this is not a trick question, what does 0.53 mean? 53%. 53%. 53 out of 100, 5.3 out of 10. About half the students were able to answer this correct. The numbers beyond that tell me the number of students that chose each of those responses. So if I look at this kind of ill-conceived chart up here, 3,698 of the students selected choice 3. 2,050 of the students selected choice 4. Yeah. That is the correct answer, because I'm thinking that number might be off. I may have to resend this to you.
Oh, sorry.
Folded right out there.
I'm sorry?
The third one folded up.
Okay. Maybe it was just that.
Yeah.
Okay. Very good. I apologize for that. If you take a look at number 14, we have a similar issue. So it's 14 is multiple choice. Again, about half the students answered this correctly. And then we can see the relative number of students that answered each of those items. If we go down to that last one, and this would be number 72 for the constructive response, if you go to page 3 for me at the top of the page, these are just broken up a little bit different. Again, I just included the columns on the right-hand side of this. I didn't include the key ideas and things for understanding. 72, 80% of the students answered this correctly. which means that 1,357 students didn't receive credit, and 5,593 students did. So out of the total pool of students that are answering, 5,593 answered, which is about 80% of that population. In the very last column in each case, the number of non-responses are indicated. So those are the students either didn't respond to this, their answer didn't show up in the Scantron sheet, or something, two responses bubble, something like that. Are there any questions about this? Is everyone fairly comfortable with the idea of difficulty, discrimination, and response pattern? We do not obtain discrimination number from state data, but that is an important part that the state collects. They go through the whole process of pre and post testing. What I'd like to do is to take a few minutes and just go through. I've got some items up here. I did not print them out, and I apologize. It'll be difficult enough to read here, but I know they wouldn't be visible on your sheet. But again, I highlighted the boxes of those numbers. That's good to look at. So what does this information tell me? What do I know, if anything, from this?
Most people got this wrong.
Okay, so over half of them got it wrong. So that's helpful. It tells me I probably want to pay attention to this at some level or another. But if they didn't get it right, where were they going? Two.
They were doing average velocity. They were assuming average velocity instead of accelerating.
Okay. The first thing that immediately struck me about this, I would be willing to bet some serious money that most of your students would be really great at plotting points and drawing lines, but it's the interpretation that's a lot more difficult. That's really where they have the challenge. And if you think back to most of the traditional labs, at least those that I've seen, they always have students plotting points and drawing lines and best fit or something like that. But we don't spend as much time extrapolating and thinking about what those charts and graphs and things mean. What are some ways that I can get at what the problem is with those students, or another way to address this? How could I use this item a little bit differently to get some more information about what students know, about what they're doing wrong, or give them the opportunity to think this through a little bit more carefully?
Ask them to show their work so you can get an idea of how they came up with their answers better. You don't know the area of a triangle.
So I could do a couple of things. Probably if I'm at the end of the year and I'm reviewing the entire test, it probably would not make sense to ask them to show their work for everything in a gradable and formal fashion. But I might want to pick a select number of items. So if this is an item that my students are not doing well with, I could ask them either to show their work for or give an explanation or explain the correct and the incorrect choices. Something like that is what I want to focus on. What else might I do?
I would suggest, show my students that when they see a graph, to try to ask themselves two questions. One would be, and they can use the units to help them out, is the slope giving me something significant, as well as is the area of the curve giving me something significant? And from that point, I think they'll be better suited to answer the question.
Okay. So take a look at do a unit analysis, dimensional analysis. Take a look at what we're actually calculating. I'm assuming everybody does activities like this, does calculations like this. They may well be closer to the beginning of the year rather than at the end of the year. So that might be one of the issues. It could be that asking 2 or 3 questions around the topic and getting them to think about what the difference between the average and the final velocity is. Might be another way to do this. That's a critical piece. So it could be the mathematical skills, it could be the way students are reading the question or not reading the question. And that could be significant for some. It could be the concept, it could be using rehearsal. Any thoughts about that? Comments? one of the suggestions that I'd like to make, it's really critical to get a handle on what the students are thinking and why that 53% missed this. And obviously, 30 students that selected the 72 and 447 that selected choice number 3 are probably going to be in a slightly different category. But it really speaks to the need for differentiated instruction and thinking about what's going on. And it's pretty significant that we have more students selecting the incorrect answer than selecting the correct answer. Rock dropping from a bridge. And again, if you want to refer back to your sheets, you have the key ideas and major understandings listed on your sheets. I was able to fit all that out here cleanly, large enough to be able to read. Rock dropping from a bridge, what happens to the magnitude of the acceleration and the speed of the rock as it falls. Comments, suggestions, observations, thoughts?
Students are pretty confident it doesn't decrease, if the speed doesn't decrease as it falls.
Okay.
To start.
If I had to make an estimate of let me just take a step back. If you take a look at tests, the way New York State has been constructing tests for a number of years, for multiple choice items with the thought that there's just a random probability, if they just randomly guessed, they'd be around 25%. What percentage or how many students might be just randomly guessing here? Is there any way we can make a guesstimate of what that number might be? Just looking at
What
those
they
numbers.
should get if they just guessed how many should answer.
If I look at those numbers, is there any way that I can get a handle? And again, it's the percentage that answered correctly, the 83. 702 chose 1, 472 chose 3, 36 students, chose 4. 5,078 selected the correct answer, and 4 of them did not respond at all. So my question is there anything that these numbers are telling me? Is there any way I can look into them a little bit more closely and get a sense of how many students may have just been guessing or how many have some serious misconception?
At least 36 of them were just guessing.
I'd say 120.
Why do you say the 36?
Because
Yeah.
it doesn't seem like anybody would come up with that as a logical answer that the speed would decrease. I think that's an obvious wrong answer that if they chose that one. And so therefore maybe there's another 36 in A and B that also were guessing, but and another 36 that guessed D.
And possibly another 36 in D. So that's why I'm going to call these estimates of that whole piece. Because this is telling me, according to New York State, Governor Cuomo, I think it is this week, said that 83% of the students answered this correctly. Probably not 83%. And if we really pursued it well and dug into this a little bit deeper, there'd probably be some level of confusion of the 83%. But clearly it's someplace in that 80% ballpark. You had 126 before.
I'm saying 160. Because I'm assuming the key is that whoever answered 3 was guessing. And then if they're guessing, you got to assume if they're guessing, about that much should guess each question.
C, so if you're going to guess, you always guess C.
So I'm spreading it out over the floor.
The other point that I'd like to make is, just about everybody's immediate reaction when you look at something like this. We assume that it was a word that was used wrong, or there was something that was capitalized or not capitalized, the font was bold, or the font wasn't bold, or they needed a diagram, or they should have removed a diagram. And we assume that these things are kind of getting in students' way. A lot of times that's not the case. As I look at this, it looks like there's a significant number in 1 and 2 that we're really convinced, both the acceleration and the speed increase. And this is a fundamental concept that students do not understand when they get to college. Guaranteed. No reflection on anyone in here. And I'm not saying they understand it when they leave. I'm saying they don't understand it when they're born. So there's something worth a little bit more digging into. How would you address something like this? How might we address something like that?
I mean, I see it all the time in my classroom. It's not a misunderstanding with a falling object. It's a misunderstanding what's the difference between acceleration and velocity. They have an extremely difficult time understanding what acceleration actually is, and need to explain that further. I mean, if you wanted to get what was going on in their heads, ask them to justify their answer. Say like, why did you pick what you picked? Write a sentence.
Brendan, have you talked about whiteboards in here?
No. Well, I mean, we've talked about it, but we haven't done any, and the group's a little bit different every time, so.
Okay. Quick question. Those of you that are using whiteboards, how do you use them in the room? I'm talking about the small panel.
We have groups of students work out their answer, and then we'll pick groups either randomly or put them on the board, and they'll talk about their answer, how they got to their conclusion, and then we discuss it as a class.
So let me just put it in a little bit different context. It's an opportunity for peer discourse. It's a chance for them to talk to each other. If you're using clickers, it turns out it's the same type of process, but it's the same type of idea, just a little bit different context. If you use clickers to respond to those page Keeley types of questions we talked about, or one of these would be great questions for review to put up and to actually post what the anonymous responses with the clickers are. Because the students don't feel any compunction about answering honestly, but nobody knows who clicker number 23 is in this particular piece. If there's something that I'm concerned about the class understanding, if I come up with results like this, then the next step becomes at your individual tables with a piece of butcher paper or a whiteboard or a couple sheets of paper, discuss this and try and reach consensus about what the correct answer is. The constraints that we're going to use for something like that are roughly about 85% and about 15%. If we have something more than 85% of the students in the room answering the question correctly, well, it's probably marginal because there aren't that many students that want to be impacted with that type of discussion. Likewise, if I have less than about 1 in 5, 20% or a little bit under that, there aren't going to be enough students in the room to actually carry the discussion forward. But if I'm running between that 15 and 85%, it's an indication that I should close my mouth and they should be talking to each other and working through constructing their own understanding. Because chances are, I've already said something that's a correct statement. My saying it louder probably will not be the right answer. But having them think about it and work through it and put it in a little bit different context would be quite helpful. Comments, thoughts?
I just have one comment. Some of the meetings I go to, the students that don't want to show that they don't know the answer, you can sometimes say, explain why somebody would come up with that answer.
Absolutely.
Oh yeah, I know the right answer. But explain it.
Absolutely. And I'm assuming, I haven't taken a poll, but I'm assuming most of us are all in a wide range of situations. I know I'll go into some schools and they have more technology than you can walk around conveniently. And other schools have absolutely none. But the clickers, thumbs up, thumbs down, holding up little pieces of paper, all the rest of that, all kind of get to the same point. The clickers are nice because they're anonymous. They really kind of take the student off the hook for how they're responding. And then they can get a sense of what's the whole class thinking, how's the class doing as a whole. In some schools, in some classrooms, they're actually using clickers to do the tests and have students with particular clickers, you can do this. They take a self-paced quiz and then turn in the answer sheet as well. And the benefit is that the clicker set up the clicker software program test will have that multiple choice answer before they walk out of the room. So it's a little faster to scan around. Any other comments or questions or thoughts?
I'd like to add, just because of that type of question, something that I use, there's a particular program, the physicsclassroom.com, that was produced by a teacher in Chicago called Minds on Physics modules. And what he classically does for his small modules is he takes misconceptions like that one, that a student thinks, well, obviously anything that falls faster to the ground is accelerating faster as it falls. And really makes these students, they keep saying to themselves, why do I keep getting this question wrong? Because the two things, one for the misconception and two for the point that they don't want to take the time to read the problem correctly to make sure exactly what they're asking for. And I feel that gives the students a lot of structure for not falling for misconceptions or simple wording in problems, trick wording type of things.
What are some techniques we could have students do if they're not reading the questions? What are some things you could ask the students to do or require?
We talked about this at our earlier meeting, is if it's a passage, you have them take what the question was and underline where they found the answer in the passage and put a number next to it.
So underlining, circling,
Yeah.
diagramming, all the standard things that we're doing that they never bothered to do.
Yeah.
They do it when they get to the test and stuff oftentimes. But emphasizing those things, and if it turns out it's some other issue, then reading's not the answer, then that helpful strategy. There was also a program called Physics for Everyday Thinking. It was initially put out as Physics for Elementary Teachers. They do a wonderful job of kinematics in particular. And it's the most effective use I've seen of motion detectors that have students actually go through the process of determining is there a force acting on this car that's moving down the track at a constant acceleration. They really focus on looking at graphs and interpreting graphs and charts. Thank you. How about thoughts about the next one? So 4 identical projectiles launched at various angles above the level ground, which represents the initial velocity of the projectile, largest of total horizontal displacement. Any ideas or thoughts? 75% of our students were answering. Correct.
Kind of verifies what probably we've all seen, is the most common misconception is the lower angle will go the farthest. And then you got kids who are just going, well, 70 is the biggest, so therefore it's going to go the farthest, but that's not nearly as big a problem. I would say that 60, anyone who picked 60 was probably just guessing, because it kind of falls in between everything and just doesn't make sense. If you know 45, I try to get the kids to play the old track and field games and Nintendo, because if you do that, you know from, at least when I was 7 years old, 45 degrees is going to go the farthest.
Let me ask you a couple of things. Think about the lab activities that your students have done with this topic over the course of the year. Are they a really strong set, or are they exploring multiple issues? Which one gives us the greatest vertical component, which gives us the greatest horizontal component? Changes around in terms of how you're phrasing this question and asking them to justify, so there can be a whole series of questions. Realistically, that might be the set that you want them to think about this type of problem with. So they're thinking in a little bit broader context with those particular pieces. So I guess I'd ask you to think about the lab activities that you're doing, the nature of the questions that you're asking. I'd also like to share with you one of the most frightening experiences in my life that happened about 2 years ago. A friend of mine told me, made a statement, and I absolutely thought it was crazy and didn't believe it. And I asked some freshman students I had in a fairly large lecture class of 100 students taking the survey course. And the question started out like this. You showed a picture of a beaker with 100 grams of water, and you showed a carboy with 20 grams of salt. And the question is, when you dump the 20 grams of salt into the 100 grams of water, what's the mass of the mixture? The most common answer? It's obvious, less than 120. Slightly less than 120, because salt's dissolved. You stir up the mixture until the salt completely disappears, until the salt completely dissolves. What's the mass? Well, it's still going to be a little bit more than 100, but not much. Obviously not going to be 120. which is really great news, because I'm thinking now we can just get rid of mercury from people. Running lots of water down the drain. This could work out really well. But it really is a very frightening thought that students that are trying to tackle the structure of matter, things, don't have an idea of conservation of mass. And if you think about it, a lot of the experiments, I know in physics it's a completely different situation, but a lot of experiments that are done, if they take the boiling point of water in a classroom, they might come up with a 20-degree variation among the classroom. So we're using equipment that's marginal to begin with, and they oftentimes don't get numbers that are realistic. And what's the answer become all this? Page 63 in the book, it says it's supposed to be 14.2. Or where the teacher said the answer is really 14.9. So in fairness, we don't really give them the chance to go through and really value their own experimentation and the data that they're collecting.
I'm just wondering if there are any baseball players that say, I hit the ball, it's not 45 degrees, it's 30 degrees. And when you include air
Or
resistance,
golf, I mean,
or golf,
it's
you know,
13 degrees.
that they're sitting there going, I have, physical intuition, and they're telling me to ignore physical intuition and go to this artificial, there is no air resistance.
Good point.
That's part of the reason for the choice one selections. And I'm looking at the difference between C and D, and I'm thinking vocabulary. The 219 choice fours are because they forgot horizontal means this way. My daughter, which one's horizontal, which one's vertical?
Could very well be, and I need more information. And the difficult part of this is that these students have graduated, that they're off to college. But the point is that if this was a challenging question for the students last year, unless I do something differently, it's still going to be the same level of challenge for the students this year. So I can get a sense and actually build a database over time here. I get a sense of pool of questions that relate to a particular topic or concept. I can get a sense of what the issues are that the students are having with misconceptions. Any other questions, comments? Once, going twice. This was another one from a similar topic. This was about 45%. This one is dealing with two-dimensional motion and asking them to calculate the amount of time the air was in the ball, or the ball was in the air, excuse me. And if we take a look at this, we've got about 45% answering correctly at 3.06 seconds. We have about 3,510, significantly greater number, suggesting it should be 1.53 seconds. Friction.
Well, we were just saying these are the ones that drive you nuts as a teacher, because it's like they did the hard part. They just didn't think about. I mean, the math is usually the problem.
Yes.
And they forgot.
They do all the hard stuff, and
Yeah.
then it comes to the easy thing.
And the obvious thing, which it has to come back to earth.
So the question again is going to be, how do we drive that point home? How do we get them on that piece?
Picture.
Next
Draw a picture. I mean, sometimes that's
Next
doesn't
step.
quite
So drawing a picture, having them go through some type of broader thing, this is what's happening over the course of the whole trajectory, and making certain that they have some skills in place that kind of carry them through that part of the process.
Just on that point, I mean, I don't know if anybody else sees that, but I definitely see a distinct lower scores for my kids on multiple choice compared to the part twos, when they do get to show kind of what they know and have the room to do this stuff. I think that's a good point. It's just telling them to treat these multiple choice questions as if they were constructed responses. And if they are willing to do that, I think right there you'd see a lot of problems with this probably.
Well, and again, I'm thinking you could do a couple of different things. If you have the clickers, you could obviously take the students through this and show the question first, and then show them what the responses were in their class. You could also take the class, show them this, this item, have the answer, and then show them what the responses were, and ask them to respond what the students did wrong. Those 20, those 35, 110 students do or fail to do that they should do. And again, it's a small task. It's forward. I've got several more of these. What I think we'll do is let's take a look at this one, then I'll jump to a couple of the constructive response. Jump there. Showing the diagram below, the box its contents and combined mass of 5 kilograms, horizontal force of 15 newtons required to push the box to 1.5 meters per second. Inertia of the contents of the box increases if there's an increase in. Several years ago, there was a question about which has the greatest inertia, and I think it was the first one. The first one they had in a while, and they were asking about a football player that was very massive, that was sitting still, all the way down to a cross-country runner that was very light, running quick. And I don't remember the results, but I want to say they were less than half of this. I suspect this is one of those topics that we've been hitting a little bit more effectively. What I'd really like to know is what the students who didn't answer this correctly were thinking and where they came from. So once again, this would be an example of something where maybe your students did very well on this, maybe everybody else's students did well and yours didn't. There could be a discrepancy. But it'd be very interesting to again go back and think about what are the activities or things or experiences that they've had.
On this one, it seems like there's a much more equal spread among the wrong answers than on the other ones, which kind of leads me to think that many people just guessed, that they said, you know what, I don't know why all these numbers are up here, and they're asking me this question.
Could
they
be.
all guessed.
And they're very active for inertia and momentum, so which makes mass and velocity either. So, that part kind of fits. But let me skip ahead, if it's okay with you, to a couple more questions. I think we have constructive response. This was the first one. Yes, I believe 69 is the first one I wanted to do. I kind of go into the same thread. While the plane heads due east at 1.5 meters per second, sounds familiar. While the wind blows due north at 0.7 meters per second, scale diagram represents these vector quantities. 69, determine the angle between the north and the resultant velocity. 65% of the students answered this correctly. So we have nearly half of the students that are not answering this correctly. Do any of you, completely unfair question, do any of you remember grading this last year?
Yeah.
And how students responded when they were losing credit? How were they losing credit?
I had a direct opposite. The reason why they lost credit was because they looked for the cosine, or they looked for the, they looked for the angle theta off the x-axis, because that's how the majority of problems they solve. They directly pick up the protractor and they take the angle right off the horizontal, and then they write it down. I had a student, he only missed 2 problems. Yeah, he only missed 2 problems on the whole test. This was one of them. He measured, he just did that angle. And the other one was where you had the law of reflection come in, where they, instead of having like this and out, they tilted it. And even when I looked at it the first time, I was looking at, you had the 4 angles. I said, well, and then I took the protractor out, I'm like, oh man. I'm like, it appears that this is the answer, but if you actually take a protractor and take the time to measure it, that's not the answer because they had tilted it. Those were the only 2 that he missed on the entire test. And I gave the same question for the midterm, and I still, even though we did this as a sample problem in the middle of the year, I still had students, after I explained it, that when they went through this, they automatically just wrote down the angle off the x-axis without thinking it's off the north.
So that idea of having multiple experiences, having go through this multiple times, is really critical to that process. I remember working with classes on a project several years ago, and it was kind of intriguing because students, it was Snell's Law, and they had to do some, they had to complete a data table, do some graphing. I was guilty of that. And I ran into two, it was a fairly large sample, several hundred students from across many different levels of schools, and it was interesting because in some classes they had difficulty graphing. Some of them had difficulty graphing because they hadn't graphed anything all year, ever, at all. There was another set who had graphed considerably, but they only used Excel. They were used to using programs, and they weren't used to actually graphing something by hand, and actually using calculations by hand. So it speaks to being able to rehearse with the tools and make certain that we're well on par with those tools. And with the items that they need to be familiar with. Keep thinking about the states. I forgot, what was it this year? Dancing pineapples and talking.
Yeah, the talking pineapples eaten by moose.
There'll be some questions, I'm sure, that they're going to try and put a little bit different spin on to see if the students can think. And that's a legitimate piece, but it is a bit different than we're used to seeing. 53, 54, and 55 all fell into this category as well. In this case, about 81, 85, and 90% of the students, they wanted a calculation of the magnitude of the force of friction for 54 and 55, including equation and substitution, and they wanted students to determine the magnitude of the normal force. Any comments or questions?
Yeah. How can 54 and 55 be different? Because isn't that a 2-point question? I forget how
The
they
first
score.
part, they probably didn't put the units in their substitution, but for the answer, they probably did. So they got
No, I understand how they could get 1 out of 2 points. What I can't understand is how we would separate.
it's 0. So they didn't get any points for
They're
the
bubble
equation
separate.
and substitution.
Yeah,
They got a point.
Okay, another way of answering that is.
because it used to be 1 or 2 point
Yeah,
question.
I could have showed the data for these two things combined as an average.
Okay, that makes more sense. Why? Because it doesn't distinguish
They've
why.
arbitrarily broken it up into.
Okay, yeah.
I believe. Just
That was annoying when that happened.
And in the past, one of the.
More
Like,
polling.
it's 2 questions.
And in the past, there've been a number of discussions, and that's been one of them. But it's been difficult, just a bit more difficult sometimes when you deal with multiple ones.
Okay, so I'm just trying to wrap my brain around that.
This one was similar, another 2 points for 2 questions, calculating the magnitude of the net forces by the frog. Again, overall, students did very well. And again, the question would be for your students specifically, what do they do?
It's interesting how that question is really testing Newton's third law, but they missed that. You know, they can solve it using the second law. So, you know, it's interesting how the state is really trying to, you know, assess Newton's third law. They're not getting it. That question.
It'll be very interesting to see how the next generation science standards are going to kind of move things along, or not with that. Skip ahead. I did mention the next generation standards are out. They're downloadable. There's also a response form. They are looking for comments. Can I ask a quick question? How many folks are familiar with, or any progressions? Megan, you can go to sleep for the next 5 minutes, maybe 3.5. This was an example from earth science, but it's really well done. Shale did some nice work with physics, but this was really pretty clear cut. Plummer and Krajek, a couple of years ago, took a look at students' understanding of day and night rotation, a little bit closer to an earth science topic here. Quite literally, they constructed a small dome. They had students lying on the floor, primary age students, lying on the floor, looking up at the dome, and then tracing the pathway of the Earth and Sun, etc. Over the course of the dome, they came up with some ideas that students seem to be generating, ideas that they seem to have. And this actually ties in very well back with the private universe minds of our own Phil Sadler from Harvard thing a few years ago, where they were talking about what's the reason for the seasons, and the college graduates, the engineering students didn't quite follow this. Same type of process, just at a little bit of a slightly different level. The interesting part about this, they're proposing this as a learning progression here, and they're breaking it down into 3 levels. So level 1, we tend to see the sun during the day, not so much at night. And there's a sunrise and a sunset that occurs. Second, continuous motion, and sunrise and sunset don't occur in the same spot. And then seasonal changes with altitude and position of the sun at noon. The interesting part of this whole thing is right here. This was a cross-sectional study. So these are not the same students. But if you take a look at first grade, the first grade students that they surveyed, right around 70%, let's say for a round number, 65 to 79% of the students in first grade got the idea that the sun rises and the sun sets, and got the idea that we see the sun during the day and not so much at night. Third grade, different cohort. So that wasn't the same group of students. It shows an increase. There's a little bit of noise with that 75%, and it was a modest sample. I suspect if we had followed this through, we would have gotten a little bit more cleaner numbers. By the time we get to 8th grade, the numbers have increased dramatically. 100% of them get the idea that the sun rises and sets by the time they're in middle school level. And they know that there's a day and a night 9 out of 10 times. Take a look at level 2. We're seeing a pretty big jump here. We're going from 60 and 30% of first graders getting the concept at level 2 to 90 to 70. Just about 100% of them by 8th grade. Look what's happening here now with level 3. The fact that the sun isn't directly overhead at noon, the fact that there's a change in the altitude, the length of the days changes. Nobody, we're just beginning to see this whole pattern move. The strength of the next generation science standard is that they're going to be basing strands on these types of learning progressions. So they're very much going to be based upon the idea that there are sequences that we need to learn things. So theoretically, we'll be teaching the level 1 ideas, making certain those are in place before we go ahead and hit the level 2 ideas and the level 3 ideas. So there's a logical sequence to this whole piece. That's really the biggest change in my mind with this whole next generation standard. We don't have learning progressions developed for everything. We have some ideas, we have some things that are in place initially, but we've got a ways to go with this. And with that, if there are any questions.
I just have a comment based on that progression.